Hi, welcome to another episode of Coffee with Bruce. Today we're going to take a quick tour through quantum computing. And what I want you to get out of this is two things. First, that quantum computers can solve problems that can't be readily solved by classical computers. And secondly, that they don't do that by trying out all the answers in parallel. So, quantum computers leverage the properties of tiny particles. Quantum computers leverage the properties of tiny particles like electrons, and they use this idea of quantum superposition. Now, the classic thought experiment to understand quantum superposition actually involves a cat. It's called Schrodinger's cat. It actually involves a cat in a box, and Lisa, unlike almost any other cat, doesn't like going in boxes, but fortunately we have a stunt cat to help us out with that. Anyway, the idea of the experiment is that the cat is simultaneously in two states at once, both alive and dead. Obviously, we're not doing the experiment, but the idea of quantum superposition is that a quantum particle is, in a sense, in both one state and another. And this obviously comes in handy when we start thinking about computing, where typically a single bit in a classical computer can only be in one state at a time. It's either a 1 or a 0. But a qubit, or quantum bit, is in a superposition of two states. Now, the way we represent this is often done using a sphere. The idea is that the top of the sphere is the 1, the bottom of the sphere is the 0, but the quantum bit, the qubit, can be represented by any point on the surface of the sphere, representing a certain probability that when you measure the qubit, you'll get a 1, and a certain probability that when you measure it, you'll get a 0. For example, if the qubit is here, then that's roughly a 50-50 chance that when you go and measure that qubit, you're going to get a 1 or a 0. Now, what that means is that the complexity of information stored in a qubit is quite a lot greater than the complexity of what's in a classical bit. Now, if you have a quantum computer with tens or hundreds of these bits, the amount of state captured in that computer is 2 to the n, where n is the number of bits. So for example, a 50 qubit computer has captured 2 to the 50 possible states. Now, that is obviously very hard to capture that in a classical computer, and it's for this reason that quantum supremacy, the ability to do things in a quantum computer that can't easily be done in a classical computer, has recently been demonstrated by Google. The question now is, can you do anything useful with all that complexity? And that's actually the really hard part. That'll have to wait for another day. But the basic idea is that you do controlled experiments with superposition of all these quantum states. And if you do it in a very careful way, you can actually cause the correct answers to your questions to reinforce each other and be the ones that come out of your quantum computer. Probably the most famous example of this is that quantum computers are predicted to be able to solve problems like factoring very large numbers, which will have a pretty big impact on cryptography. But we're quite a long way from that yet, because we need much bigger quantum computers before that's going to happen. So, promise of quantum computers is very great. What they can actually do today is rather modest, but they're just today getting to the state where some of the things that they can do are beyond the capabilities of classical computers. So watch this space. Quantum computing could have a big impact in the future. Perfect.